B31.3 Piping Construction Code. In this module, we shall summarize all the relevant sections of ASME B31.3, casting quality factor EC, weld joint quality factor EJ, pressure design of components, preheating, fabrication, assembly and erection, and also we shall go through a few tables to let you know how the open book question you can solve them. Chapter 1, Scope and Definitions. The owner user has the overall responsibility for compliance with ASME B31.3. So the owner user of the piping always has the ultimate responsibility. Inspector is responsible to the owner user for implementation of quality assurance plan, examination, testing, and inspection. Excluded from ASME B31.3 are the ones that have operating pressure under 15 psi, are non-toxic and non-flammable, and have operating temperature between -9 degrees centigrade to 186 degrees centigrade, or -220 degrees Fahrenheit to 366. For exclusion, you can see section 300.1.3 exclusion on page 2 of ASME B31.3, and we have brought this table here. So anything is within the scope, anything inside is excluded. Okay, so for open book question, you can go to this diagram on page 3 and then solve the question. But overall, if there is a closed book question, then it would ask if anything above 15 psi or more than 50 psi is excluded or included. That will be the answer. So everything inside the box is excluded. For equipment such as pressure vessel and heat exchanger, piping between them up to first flange or connection is excluded, because that would be dealt with relevant code. For example, if it's a pressure vessel, then it's ASME section 8 up to first flange of the pressure vessel. Outside that, it would be B31.3. So that's a boundary limit or battery limit. Chapter 2, design. Casting quality factor. The basic casting quality factor, just with a visual examination being done, is 0.8, but depending on the type of NDE performed as additional examination, the quality factor can be increased. For example, casting with either a surface finish of 6.3 micrometer RA, or if MT or PT tested, would have a quality factor of 0.85. Now, if the casting has been machined above this surface finish, as we say 6.3, as well as MT and PT tested, then the quality factor would be 0.95. If the casting has been machined as well as volumetrically tested by ultrasonic or radiography, you should have a full quality factor of 1. That's the highest quality factor. So for this, you can go and see page 15 of the ASME code. Let's go to page 15 and see if it's there or not. Okay. So we go to page 15. So that is the quality factor, and it's you need to go and check what this one means. So one here, the notes, you can go to notes and see the notes, and then go here and find out the quality factor, what it means. but we have just explained this in a simple manner. Now, basic quality factor is also brought in pages 165 to 350. The weld joint quality factor, for this you need to go to page 351. Now let's go to page 351. So it tells you the basic quality factor for longitudinal weld joints in pipes and tubes. So if it's a seamless pipe and carbon steel made according to API 5L, then EJ is 1. And if we say A53 grade, it's a seamless pipe, again it's 1. So A1006, and you have to look for it and see the weld quality factor. Whereas it's on page 350, it's the same thing, but with for casting quality factor. Okay. So here they might ask you a question. You don't need to memorize these tables. You just need to see where you have to go for cast quality factor EC and weld joint quality factor EJ. So if you increase the joint efficiency, you can do more NDT and you increase the joint efficiency. For example, if you go to table 3234, page 17, let's go there and see what we will find. Let's go to page 17. Here. So you can see that the EJ, it tells what type of joint it is, a butt weld, type of seam is straight, and the quality factor is EJ. And if it's electric resistance welding, so it's 0.85. So based on this, you'll find butt weld, single V, double V, and depending on the welding process, you can find the factor. Please look at these figures and tables so that you can easily go and find them. For example, as per table 302.3.4, a single butt weld with any ND examination has a weld joint quality factor of 0.8, as you can see here. So anything, it has 0.8. Now additionally, if you do a spot check, it gets 0.9. If you do 100% radiography, it's 1. We can increase joint quality factors by performing supplemental NDE for both casting and welding joints, because by such NDEs we are decreasing the risk of defects going undetected, and that's the reason. Now let's go to page 19, pressure design of components for a straight pipe. So TM equal to T, which is the design thickness plus corrosion allowance. Now we have a mil tolerance of up to 12.5% is allowed for the actual pipe thickness. That's a lot of allowance. This means that if T equal to TM, the overall thickness, then the actual thickness of pipe received could be up to 12.5% less than the TM. That is why the selected pipe thickness cannot be less than TM. So the design thickness. Remember that so you always go for a higher pipe size, so that even that 12% is less, the actual thickness still is over the TM or the design thickness or the minimum design thickness. Now we got this formula you would definitely use during the open book exam, and most of the time it comes for T for less than 1/6 of the diameter of the pipe. So pipe thickness, most of the pipes are less than 1/6. The pipe thickness is less than 1/6 of the diameter of the pipe, the outside diameter. So as you can see here, we got T equal to PD divided by 2. S is the allowable stress, E is the joint efficiency, W is the weld factor, P is the pressure, and Y is another factor, coefficient. They call it coefficient. Now, first find the material in table A1 or A1M. So to go to that table, you need to go to page 165. So this is a table starting from page 165. As you can see here, so these castings and all that, I want to go and look at one which is, let's solve one question here. So if you find the material here, right, first you need to look up for materials, for example A53. Then you know that the minimum strength is 47, 48 tensile, and the strength, and the yield is 30 here. Okay, now the allowable stress is 16 up to 100 degrees Fahrenheit. As you increase the temperature, you should look at also see if they have given you a temperature also. If they say it's 80 degree, 100 degree is 16. So this is the allowable stress that you can use up to. Now, it also, if you go to the next page, if they have given you some temperature, say 800 degrees Fahrenheit, then the allowable stress will be 9.2. Okay, and this B means it belongs to group B of the curve for Sharpie test purpose, and we will talk about this later on. So first find the material in table. Now you got A1 and A1M. If they have given you in metric unit, it would be A1M. You have to go to table A1M, which is a continuation of this table. So if you go down, you will find the table A1, and then after some pages, it will be A1M. So let's, you have to go so many pages down to find A1M. Okay. The tables A1M, you can see. You quickly scroll through and then go and find that particular material. For example, if they give you the material at 22 chrome, then the UNS number and the P number is here, and then you have to go and find at what temperature the minimum yield strength, and then this is the allowable stress, and these are the temperature. So go and find at what temperature this material is used. First find the material and then find the temperature. So the temperature chosen should be above the operating temperature given, because as you can see, when the temperature increases, the allowable stress decreases, and we should be on the safe side when choosing the allowable stress. So you should always select the temperature above that. So if they're telling for example, temperature is 130, so you go for 150 here, because you should be on the safe side. You round it up to the highest number. Okay. So E, again, quality factor, table A1B for weld joint quality factor, as we shown previously, 351. And Y is the coefficient, you can find on page 22. So let's go to page 22 to find the Y. Page 22. So you find the value of Y here. So if it's a ferritic steel, right, and the temperature is below 900 degree Fahrenheit or 482 degree centigrade, then it's 0.4. Most of the time it's 0.4. It's ferritic steel and all that, and the temperature is most of the time is. So see, this is a Y factor that you can find. So weld joint strength reduction factor is in 302.3.5, and then you should also allow some corrosion allowance here. Okay, now as the operating temperature increases, the weld joint strength decreases. You have to use this table 3.2.35 for weld joint strength reduction factor at page 20. So if you go to page 20, here you find the weld joint quality factor. So for carbon steel, less than 428 degrees centigrade or less than 800 degree Fahrenheit, this is 1. And as the temperature goes up, then you can see, say for chrome molybdenum, it decreases. Say at 1200 degree Fahrenheit or 650 degrees centigrade, it's 0.61. So you find the W from here on page 20. During the open book exam, you should know how to find and refer to these tables. We shall provide case examples in module 13, mock exam questions. So please solve them yourself by frequently to this B31.3, so you know how you can quickly find that table, because the search button is disabled, so you should know where you have to go. And what I would give you an advice is, if you go to table of content, because some 30 pages is actually okay. If you go to table of content here, you can see this is a long list of tables, like 5-6 pages. If you don't remember it, then go to tables. Okay, now you can see weld joint quality factor W. This is page 20. You can go straight away to 20. Y is on 22, and impact testing, for example, requirement for metal is on 15. Minimum sharp PV notch impact values is on 57. So you can straight away go to that. And preheat temperature. So the tables are smaller. It's just 2 pages long compared to 2 or 3 pages long compared to that, the actual table of contents. So that's a lot easier to find out. And also you can use list of figures if you don't know where it is. Don't waste more than 2 minutes per open book question. If you're nowhere, just make note of number of that question number, and chances are that when you're solving other question, you can find it. Okay, so for page blanks, you go to page 30, and you have this formula. The minimum required thickness for permanent blank is calculated by this, and everything is same except the DG, which is a new parameter, is the inside diameter of gasket. All other symbols are the same as the formula we have shown here at the top, this formula. So internal pressure, outside, and the allowable stress, and joint efficiency and weld efficiency, etc. Okay, plus C, which is for corrosion allowance. Acceptance criteria for welding inspection and NDA examination as per ASME B31.3, and you can see table 341.3.2 as acceptance criteria for welds, visual and radiographic examination. So I just want to show you how it works. So if you go table 84, Let's go and find table 84. You can see here typical well imperfections is telling you what is it, the code, and then you go here, and as you can see, normal and category M fluid service is categorized, cyclic, severe cyclic service, category D fluid service. So if you have a crack, it's A. And what A means? A means A is rejected. Extent of imperfection 0, acceptance limit 0. So anything which is A means is 0. Now if it's B, commutative length of incomplete penetration should be, the total should be less than 38 millimeter in any 150 millimeter, or 1.5 inch in any 6 inch. So if you go here and see something which is B, the B shows that that is the limit. That imperfection should not be more than 1.5 inch in any 6 inch. So the acceptance criteria NDE is in B31.3, and the NDE is according to ASME section 5, the procedure, how you do it. Now, hydrostatic leak test. Test fluid used for hydrostatic leak test of piping is water, but if water may have adverse effects such as corrosion, other liquid may be used, provided that such leak fluid is non-toxic and their flash point, that means the temperature that the fluid is ready to ignite in presence of a spark, is more than 49 degrees centigrade or 120 degrees Fahrenheit. So that is the requirement if you are not using water for test pressure. And the test pressure shall be 1.5 times of design pressure straight away. Now, if the design temperature and test pressure are different, then a correction factor may be used, because material allowable stress is different at different temperatures. Remember, we went to table A1 and we saw that the material allowable stress is reducing as the temperature is increasing. So if the design temperature, the working temperature, is some high temperature, and the test is done at ambient temperature, that means less than, say, 100 degrees Fahrenheit, then you have to use a ratio. That means the allowable stress at design temperature divided by allowable stress at test temperature. That would be the factor you have to add. So eventually the test pressure goes up. It's not only 1.5 times, it will be more than that actually, the pressure itself, absolute pressure. The correction factor would therefore be the ratio of allowable stress at test temperature divided by allowable stress at design temperature, or S test divided by S design. Now, find the allowable stress. Again, you go to table A1 or A1M. So this is like a 150 page or 200 page document just for this table, because it covers all the materials and all the temperature range for each material. So you go there and find the allowable stress in tension for metals at various temperatures. This is both metric and US units. We always use the higher temperature or lower allowable stress from the table. Pneumatic test. Gases, unlike liquid, are compressible while under pressure and store a great deal of energy. So if there is any failure during the leak test or pneumatic test, especially pneumatic test, it would work like a bomb. It would be a catastrophe. Therefore, if there is failure and compressed gas is released during pneumatic test, it would inflict a lot of damage to the surroundings, including the personnel. That's why they always either do it under the water in the underground, or they put barriers around, so in case it bursts, so it doesn't injure people. Hence, protective barrier setup, or the test is done with a tank full of water to contain the possible explosion as a result of pneumatic test failure. Pressure relief device is also attached during pneumatic test, leak test, with the pressure at 1.1 times of the test pressure. Remember, this is 1.1 times of test pressure plus 50, or test pressure plus 50 psi, whichever is less. So in case it goes over the actual test pressure is 1.1 times of maximum allowable working pressure, but here you just add 50 psi to the relief valve calibration that set pressure, so that if it goes beyond that 1.1 times, then it releases the pressure and there wouldn't be any danger as a plan B. The gas used for pneumatic test shall be non-flammable, non-toxic if it is not air, and normally is nitrogen. The pneumatic test pressure shall be 1.1 times of the design pressure. So practically, what does it mean? If the design pressure, say, is 100 psi, you do the pneumatic test at 110 psi, and the relief valve is set at 1.1 times of test pressure, which in our case was 110 psi. So 1.1 times of 110, I think it would be 121 psi. Okay, and 121 is less than 110 plus 50 psi. So that's good enough. We use the a low pressure example. If the pressure is like 600 or 700 psi or 1000 psi, so that 1.1, the reason is they put 50 psi, that would apply, because then if it's 1000 psi, you have say 1100 psi for test pressure, and then you have 1200 psi for the relief valve. Now in this case it says 1.1 times or 50 psi, so 1200 to 1100 would be 100 psi. So because this is more than 50 psi, you use this number. So the valve should be set at 1150 psi here in this case, not 1200 or 1210 psi, that 1.1 times of test pressure. First, the pneumatic test. During the pneumatic, the pressure is increased up to half of the test pressure, and the piping is checked for any leak and deformation. So up to half, 50%. You don't go straight away to 100%. Then in steps, you increase it. Once it's normalized and stabilized, the pressure gauge, wait for some time, you increase it by 10% a step, and every time you wait till it's stabilized. And then, so the total step takes 6 steps, 50% plus 10% steps. So 6, they might ask you what is the total step of pneumatic test in the exam. Once the pressure test is reached, it's reduced to design pressure, examining the piping or for any leak and deformation. So for both hydro and pneumatic test, once you reach that stage, and according to procedure, they say, okay, wait for half an hour, look for leaks, so that the whole thing is stabilized. Then at the time when you are going to look for leaks or doing some exam, visually testing the component, you have to reduce the pressure to the maximum allowable design pressure. So you have to reduce it by whatever the test pressure is, divided by 1.1. That would be the pressure that you will be checking for you're visually inspecting for pneumatic test, and divided by 1.3 during hydro test, and then that would be the pressure you will be checking after hydro test, during hydro test. You should calculate also the ST-SD ratio using either table if test and design pressure are different. This we already talked about. Lower temperature listed limits, listed materials. Again, on A1 and A1M, again, same table. This is going to be frequently you're going to be using it on page 47. Minimum temperature a metal can operate if it's either a number or refer you to correct curve in this. So if you're working with a low temperature, I'll go to page 47. See, I'm always adding 30 because there is so this graph is going to be very important. Okay, so first you go to table A1A or A1A to find which group is it. I told you in previous table that it says group A, B, C, D. Then once you are in that group A, B, C, D, they will also give you the thickness of the metal. So you see which thickness is it in millimeter. There is one, I think, in millimeter and one is in inch. You can see another table in inch. Yeah. So say for millimeter, I'm just looking at it. And then, you know, the degree centigrade, the temperature is actually the working, the minimum design metal temperature is. So you draw a line here, like imaginary line, and come here. So if you say 40 millimeter and the temperature working is 10 degree. So impact test is required because it's below the curve and it's say on curve A. Okay. Now, curve B, sorry. Now, for curve A, definitely required. For curve B is here, for curve C, for curve D, depending which curve that material belongs to. So that depends on toughness of the material. So they will have 4 curves here. Now, if it's curve B, but the temperature is say 20, above the curve, you come the point that it intersects the thickness versus the working temperature. Then it's above the curve, then no impact test is required. So it asks you whether you want to find out whether impact test is required or not. Okay. So we have explained here, we brought an example. Please go to this table and use them and read our explanation here for this material and see how this works. And we have also brought this here on page 50, which is in millimeter, and so you can find the inch versus this on the subsequent graph. Test specimens, each Sharpie test. So if impact test is required, that's a Sharpie test, 3 specimens at minimum design temperature. So table 323 shows the minimum required impact test values, 323 on page 57. Let's go to 57. So 32335. So we go to 57. This is the reduction. So if they tell you that the full size is, this is the full size. So if the you have to use a reduced because it's 10 millimeter by 10 millimeter by 55 millimeter, the Sharpie impact test. So if the length or the size is reduced because of the pipe is too small to get a sample out of it, so you have to reduce the temperature also. This is temperature reduction accordingly. So if it is, say, you have to do the test at say minus 20 degree and it's reduced 3/4 of size bar, so it's not 394 inch or 55 millimeter, is 295. That's the maximum you could get for this sample. Then you have to reduce it by 2.5 degree Fahrenheit or 5 degree Fahrenheit, 2.8 degree centigrade or 5 degree Fahrenheit. If it's reduced further, as it's reduced further, say 1/4 inch of the size bar, you have to decrease the temperature by another 50 degree Fahrenheit or 27.8 degrees centigrade. If the size of the specimen is like a quarter of the normal size it is, because of fabrication difficulty, the pipe is too small, etc. So this is the size. So let's go the minimum value. Minimum value you can find here. So it tells here, for example, any material with 448 megapascal of tensile strength. So you need average of 3 specimens. The in joules, if it's fully deoxidized, then it's 18 joule, and the minimum is 14. So what this means? This means that the average should be 8, should not be less than 18, and no specimen should be more than 14. And it's always said not more than 2/3 of the average. So this is straight away tells you, once you get the result, you see whether this result is acceptable or not. So if you go, if the material is any material with a strength of 448, as you can see that the strength increases, the minimum value required is also increases, because when you increase the strength, the toughness decreases and the ductility decreases. That is normal. So if a material is, say, 5117 up to 656 MPa, so you have 3 specimens, one should be, the average should be 27 joule, and no specimen should be less than 20 joule. Even if the average is 27 or more than 27, but one specimen is less than 20, then still the test is rejected. Okay, so we brought example here, a few examples, so you can see what's going on. Please again go to these tables and frequent them. So again, this table is the acceptance criteria for average values, and we have explained it in detail here, and we brought different scenarios to tell you that there are 2 requirements: average value, minimum value of 3 specimen, and 2, the minimum value for each specimen. So in this case, for 448 MPa up to 448 MPa strength of materials, 18 joules, and no specimen less than 14 joules. So there are 2 requirements here. These tables are very important. Please make sure that you got them. Preheat temperature shall be checked by crayons and thermocouples, pyrometers. So this term might come, how you check the preheat temperature. That include weld area and at least 3 inch or 1.5 T away from the weld. For tack weld is 1 inch. So the preheat should be maintained at least 3 inch or 1.5 T or thickness of the base metal away from the weld. And it also, if you go to page 72, it says what is the preheat temperature. So table 330.1.1, so 72, let's go to 72. So if you go here, you can see the preheat temperature. For example, for carbon steel less than 25 millimeter or less than 1 inch thickness, the required minimum temperature is 10 degrees centigrade or 50 degrees Fahrenheit. So depending on different materials, you can find the preheat temperature here. Very easy. It's just, you should keep insisting that you should frequent these tables, because once you know where it is, it's very easy. Just go. It's even the open book question are even easier than closed book. Closed book you have to memorize, but the open book you should just know where it is and go and find it. And thermal expansion, this is definitely a question coming from here, page 392. So I want to tell you how this works. (392). So if you see this thermal expansion, This, you can see the group number, which you can find from A1A table, group 2 alloy steels, and they brought two coefficients of thermal expansion. The first one says that, for example, I'll tell you how to use this table. For example, you got 400 Fahrenheit and you got 70 Fahrenheit, you increase it to 400 Fahrenheit, and you want to see what's the expansion here. So the top one tells you that 7.1 minus the bottom one tells you 2.8 minus 0, which is 2.8. So for every 100 feet straight away, you can see that you got 2.8 inch of expansion of the pipe. Now this one tells you, you can calculate this also. So 7.1 minus 6.4 into this number. So that into 100 feet would give you again the 2.8 inch. We have solved the problem here. So this tells you straight away what it would be. And the exam question, the answers are too far apart. They're not like very close to each other, so you should get the exact number. So as long as they want to know you get the approximate number, that's good enough for them. So here we have solved this linear thermal coefficient, say for group 1, 2.8 inch 100 feet. Now, if you use the corresponding value, 7.1, 400 minus 70 into 7.1. So if you have to 400 minus 70 into 7.1. That's what you get for exactly 2.8 inch. Or not exactly, but it would be very close to 2.8 inch, and hence that. So you need to know where this thermal expansion data is. Last thing is, each employer is responsible for quality of his welding, qualification test of his WPS, qualification of his welders. WPS and WPQ shall meet the requirements of ASME Section 9. Employer business name shall be on the WPS. WPS shall be signed and dated by the employer, thereby accepting responsibility for the WPS, even though the qualification is subcontracted by others. So a pipe ASME code allows that the manufacturer subcontract this, but then he has to take responsibility, or he can say that I've subcontract part of the building and all, or the manufacturing to somebody else, but he has to sign it off. The ultimate responsibility lies with the manufacturer. Avoid duplication of effort, and the employer may accept the WPS qualified by others or welders qualified by others, provided such evidence exists and available to the employer, and employer takes full responsibility for approving them by signing their welder ticket or the WPS. The employer shall maintain the welding and welder qualification record and make it available to the authorized piping inspector. And you can also look at the joint profiles and limitation to familiarize yourself with the joint dimension. For fillet weld, there might be some simple calculation. Theoretical throat is equal to 0.707 into leg length. So remember, this is a theoretical throat. They might come and say there is a concave fillet weld with a weld reinforcement of so and so. So that reinforcement you have to reduce from that, so you get the theoretical truth. The preheat temperature may be reduced to 95 degrees centigrade minimum for the purpose of root examination without reapplying So normally, if you are also need to have a interpass temperature, which shouldn't be more than 600 degree Fahrenheit for metallurgical reasons. If you want to examine the root visually, you can reduce it. Whatever interpass is, maximum should be 600 Fahrenheit. You can reduce it to 200 degree momentarily, so you can close in and visually inspect the root. without again reapplying the interpass temperature and then continuing it.